thanks for inviting me, Vivek. And so I also want to thank you and the rest of the organizers of the club for putting together this great seminar over the summer. I know a lot of us have been kind of swamped with all the COVID stuff, and then others of us are stuck at home and are very eager to kind of have access to this stuff, even when we're kind of it feels like a lot of the world's on hold. So thanks a lot for putting this together. And I, as a representative from the Utah Center for Data Science, again, let me just say, if you ever want, any help organizing Prince-a-thon, we're more than glad to be partners and supportive of that.
I totally appreciate that. Thanks a lot.
Sure. So let me start with the talk. So this is a primer on the geometry of machine learning, and so as Vivek was explaining, I've been doing a bunch of stuff in education, especially, and research in data science here at Utah. But my PhD area was in computational geometry, and so I still work on aspects of computational geometry. And so this is based on a talk I gave last year, about a year ago, at the main computational geometry conference, where I was trying to explain to a bunch of geometers who are mostly of the theoretical nature, what is machine learning in terms of their language and way of thinking. And so I thought this might also be an interesting talk for a lot of you, because it'll give you hopefully either a great geometric intuition to these concepts if you haven't seen them, or if you have, then kind of a different viewpoint of like a bunch of these things. So I'll start off with mostly a lot of fairly general work, and then I'll get into kind of how some of my research has fit into this viewpoint at the end of the talk. So starting off, what is machine learning? So kind of machine learning is very broad. It means different things to different people. There's supervised or unsupervised, where you don't have labels. You do things like clustering, or like dimensionality reduction. Clustering is finding sets. Dimensionality reduction is trying to preserve the values while reducing what the dimension is. And then if you have labels on your data, then you're getting into things like regression, where if the label has scalar quantities, then this is kind of regression. You're trying to predict that scalar quantity. Or if it has a class property, then this is classification. Your positive and negative points, you're trying to build a function, and you're trying to kind of predict what the sign is going to be on points you haven't seen yet. Okay, so there's lots of geometry in all these areas, but in this talk, we're going to talk about the core thing of classification. And if, in the educational program here, we mainly put this in the machine learning class, and a lot of the other stuff falls in the data mining and other classes as well. And I'll do a plug. I've been writing this book. It's been taking a lot of time. Hopefully send this to the final version to the publisher in the next week or two, and it might be available for print by the end of the year. But if you want to learn more about this, you could just take any class from me, and it's basically the class notes is what's turned into this textbook. So what is machine learning? Let's start and formally define this in some geometric way. We'll start with the point set in RD, X points, and each of them has a sign function. I'll use sigma for this, and it's either -1 or +1. So I've drawn a bunch of points here. They're either minuses in red or pluses in blue. And now the goal of classification is, in the linear separator, is to find a separating half space, right? So a half space is half of the space, right, divided by kind of a line, or in higher dimensions, kind of a half plane. But then the green part that's shaded in, you want to say anything that falls in there, you predict is going to be a positive point. And so you want to find a half space that contains all the positive points and none of the negative points, right? And so how do I think about this? I can find that there are a bunch of these different half spaces I could find, in fact, in this data set. One way of thinking about is the margin, which is the distance, the minimum distance from any of the data points to this half space, right? So that little purple arrow there, that's the margin of this half space. But it turns out what you want is not just any one, you want the one that has the maximum margin, right? So you want this as big as possible. And it turns out on new data you haven't seen yet, this one tends to work better because you're not kind of close to the boundary of cutting stuff off. You're as far away from what you know of the boundary as possible. Okay, and so you want to find often the max margin linear separator of data if you can find that. Some nice things about this is that it's always sufficient to define this with only d plus 1 so-called support points. So in 2 dimensions here in this picture, there are 3 points. D is 2 and d plus 1 is 3, right? So there are 3 points that define this. And if I try to wiggle this anyway, it's only going to get smaller or cross over one of those 3 points. And so one way to find this from a geometry point of view, the first thought might be, okay, I'm going to check every combination, of d plus 1 points, check, build the max margin defined by those d plus 1 points, check if it's a perfect separator, and if it is, find the one of those that has the maximum margin. And this is one way to find it, but this is a pretty big polynomial as d gets large, and in machine learning, d is often large. Okay, so that's one way to solve it. Kind of a different way, a different geometric way of thinking about this, and I'll eventually get to more traditional ways of machine learning, but let me start with the geometry way, is to think of the convex hulls of the data points. And this is, if you haven't heard of this before, think of putting a bunch of nails in a board and put a rubber band around the outside and let the rubber band shrink, right? This defines the convex hull, and do this for the positive points and the negative points. So do those separately. And in high dimensions, this is called a polytope instead. So you can do this in high dimensions. And so you should be thinking about this in high dimensions, even though pictures are in 2D. Okay, and so then I want to find the minimum, the 2 points, P in the positive region, Q in the negative, P and Q here, that are as close together as possible. Okay, it turns out that the line between them is twice the margin, and the bisector of this purple line here is exactly the classifier that we're hoping to find. So this is an alternative geometric view of this problem. And so you can write this down. It's there's squares in the distance function. So this is a quadratic program. Turns out you have to lift it to 2 plus d, 2 times d dimensional space, but you can write down as a quadratic program. So as a geometer, I don't like quadratic or linear programs or mixed integer programs, stuff like that. I think those don't provide a lot of intuition. So I'll discuss a different way about how to solve this problem. Okay, and so to think about it, we again want to find this notion of margin, but to understand this properly, because margin scales with the data, we're going to assume that all the data has the vectors of the data points have norm at most 1. So they're all inside the unit ball. So if they're too big, you can shrink them down. Okay. And now we'll define the margin with respect to these shrunk points, and this is gamma. Okay. Or it's in this case it's the min. Okay. So I wrote it as the min distance, but it's off by a factor 2 of this. Okay. And now we can solve this problem approximately with the number of steps, which depends on gamma and the error in the approximation. I'm going to find a margin which is going to be slightly larger. I'm going to find P hat and Q hat, these approximate points, and their distance is going to be most of 1 plus epsilon larger than the minimum. And I'll do this in number of steps that depends on this epsilon and this gamma distance. Okay. And so this is kind of a very old algorithm as it turns out. And how this is going to work is I'm going to start with any 2 points, in this case Q6 and P3, 1 in each polytope. Okay, so I know this is a feasible solution. And then I'm going to trick the direction in the green arrow from the positive to the negative and find the most extreme point, let's say that's P5, in the positive polytope. Okay. Now I'm going to look at the line between the old point in the positive polytope, which is P3, and the new point, P5, and find the minimum distance from the negative point along that line. Okay, this should be perpendicular, but think in high dimensions, pretend this is perpendicular. This will make the drawing a bit more interesting. Okay, so this is the minimum point on the dash line to the point in the negative polytope, and this is one iteration. Okay, and then I do this the other direction. I look from the negative polytope to the positive one. I find the most extreme point in the negative polytope. I find the line between the old point and the new point, and I find the minimum distance. That's my new point, the negative polytope. Okay, and I repeat this other direction, find the minimum point, and I do this back again. Okay, and this is guaranteed independent of the dimension to succeed in 1 over epsilon times 1 over gamma squared steps. Now I'm going to find a 1 plus epsilon approximation, or 1 minus epsilon approximation of the minimum distance, which corresponds with the max margin so separator. So this is called Gilbert's algorithm from 1966. So this is pretty old, and it was kind of effectively not quite rediscovered, but reanalyzed and tightened a little bit in the computational geometry community about 10 years ago. And in addition to this, one of the things they pointed out is that this corresponds with the classification problem. So okay, so this is one way of solving this. Yeah.
Yeah. So the P and Q can be inside the polytope also, no? It's not just the boundary points on the polytope.
Yeah. So I mean, in general, you're going to want P and Q to be on the boundary, but actually on the right boundary. And so in this picture, in 2D, this would actually end after a small number of steps. It would find the exact answer, right? So if you have a good bounded dimension, you can end earlier. But in high dimensions, it's going to be kind of floating around in the middle or on the boundary someplace of the polytope typically. And so this is kind of what it looks like in high dimensions projected down to 2 dimensions. So that's kind of what I've drawn here. Yeah. So good question. Yeah. This is typically not how this is thought of in machine learning, but as we'll see, there's this Perceptron algorithm, which you may have heard of, which is very related to this, and is essentially the same thing. And let me now explain transformation you need for this, and then we'll go through a geometric view of this algorithm as well. So to talk about the perceptron, I need an additional assumption about the data. I need to force the half space now to go through the origin to run the perceptron algorithm. But it turns out that's like shrinking it so that the norm is at most 1 of all the data points. I can do another transformation here. And what I do is I basically, in the d plus 1th coordinate of every point, I add a 1 to all of them. And so a geometric view of this is I've added an extra coordinate up in the plane, or maybe coming out of your screen, and I've lifted all the points up in this 1 dimension. Now the origin is at the kind of those gray arrows, the base of those gray arrows. That one is not in this plane. But now a half space that goes, the boundary of a half space that goes through here, it can now, when it passes through the purple plane where all the original, the d-dimensional plane where all the original data lies, it's still a d minus 1 dimensional kind of boundary in there, and the points which are positive are still kind of a half of this d-dimensional space. Okay, but this one now can go through anywhere, right? By rotating and translating this new lane, you know, even though it has to go through the origin of the d plus 1 dimensional space, it can go through anywhere in the d-dimensional space. Okay, now there are some weird issues with like the notion of margin. I've changed this by up to like a factor square root 2 in some region. I have to first normalize and then I have to do this, but it's off by a constant factor. Okay, so you know, if you buy this, there's this geometric transformation and up to constant factors, I haven't really changed the problem, but now I can assume the half space goes through the origin. And if you know, this is the same thing as having an offset and increasing the vector by 1, but this is just the geometric view of this transformation. Okay. Okay, so now the picture looks like this instead. Now all my points are inside a unit ball, right? The pink ball is a unit ball, and I've normalized it so the furthest point, this minus point up here, is exactly distance 1. I've shrunk them to that, and then I've done some transformations so it must, you know, I've added this 1 dimension, so it has to go, the half space has to go through the origin. Okay, now I can assume that my separator, the black line in this case, now goes through the origin, and I can be sure this is as powerful as I was before without having this restriction. Okay. All right, so now we can talk about the geometry of the Perceptron algorithm, which is one of the earliest, kind of, if not the earliest, so learning algorithm for classification other than, say, these square stuff. Okay, and they have these 2 assumptions. Okay, and so what this does is it starts with any point, kind of one of the data points, and I have defined a direction W towards this data point. And something critical about the Perceptron algorithm is it uses that this can define a normal direction of the half space. This green arrow defines a normal direction of the half space. And a data point is a d-dimensional vector, and a normal vector, or even if it's not an not unit vector, that's also, I can store both of them as arrays. I have this duality between a point and a vector, and that this is critical for the Perceptron algorithm. So okay, so now I have this, and so I can choose any point as my initial normal direction. And then, so this is from Rosenblatt in 1958, so even earlier than Gilbert's algorithm. And if it is a negative point I chose, I multiply it by the sign, right? So I'm multiplying it by the sign, so then I'm still pointing towards the positive points, okay? And then I iterate, again, 1 over gamma squared steps, where gamma is this margin, and let me go through these steps here in an animation. I find any point which is misclassified, this plus point, and what I do is I just add it onto my vector W. I add the vector towards that point, right, is this green dashed line here. I add it onto the old vector W is here, and I'm adding it out here, and I get a new vector W. This happens to be normalized, but that's an accident. Okay, and this is my updated classifier. The classifier is then the boundary, which is normal to this vector. Okay, and it turns out I've misclassified fewer points than before, but I can still find one, so I repeat this. As long as I can find one, I repeat this. Now it's a negative point, so I'm basically going to subtract its vector instead. Okay, so I've taken this vector towards this point, and now I've subtracted it here, and I get an updated vector W. And this maybe is about the same as before, but I guess it's better in some sense. And so I've updated this again, and I find another misclassified point. It's negative. I subtract it again, and I add this again. And at this point, I have no more misclassified points, and at this point, I can stop. Right. Right. So this is how the Perceptron algorithm works, and it builds a linear classifier in this way. So okay, so this is almost the same as Gilbert's algorithm after some transformations. There's some nuances, but they seem very similar to each other. One thing we can learn from Gilbert's algorithm, which is not, I think it's becoming more widely known in machine learning, but probably I get the sense it was not widely known about 10 years ago, is that if I change this, so I pick the most misclassified point every time. So I change this to an argmin instead of any point. And I do it for an extra 1 over epsilon factor steps. Then I can guarantee that the margin I find, not only will I guarantee to find a separating hyperplane if there exists one, but I guarantee that it will be 1 plus epsilon approximation of the optimal one. So I'm guaranteed to approximate the max margin hyperplane if I run this by always choosing the furthest away point. It's a little bit more time consuming to do. I can't just loop through sequentially. I have to loop through all the data points every time to find the furthest. And it seems hard to kind of actually speed this up from an algorithmic point of view. But you know, this is a small number of steps. So a small number of steps, I scan through all the data points. And if I do approximately the furthest, it should work, but it seems hard to find the approximate furthest. But so, okay. So this worked if the data was separable, if there exists a perfect classifier. But that's not always the case. So in geometry, we would think about this as if the two polytopes were overlapping with each other. If they're overlapping with each other, there's no way to separate them. This is an equivalent way of thinking about this. And so what should I do in this case? And so there are a couple of kind of ways that this is dealt with. You can make it a nonlinear thing through kernels, or you can add some penalty term. And I'll kind of more briefly talk about both of these again from the geometric point of view. Okay, starting with kernels. I have a question. Yeah. So,
Perceptron doesn't guarantee that you get a max margin thing. Like it just guarantee you get a separator if things are.
Yeah. What the Perceptron guarantees is that if there is a separator, and after you've normalized the points and the margin is gamma, after 1 over gamma squared steps, you will find it.
Okay.
That's what it guaranteed. The proof isn't too hard. It's more technical. I'll go through this talk, but it's in the book.
Okay.
But it doesn't guarantee anything about how good the margin is.
Okay. Thank you.
Yeah. At least I don't know of any guarantee of that. Maybe it's possible. It's not going to be very good. Yeah, because once you effectively don't have any more points to choose, you don't know what to do, and you might have found something that is very close to one of the data points. Whereas in the thing where you find the argmin, you can even find something that's classified correctly, but is still close to the boundary, and use that, and that's what you should use to keep running. So I will find a perfect separator before I'm done, but I will keep running it, and I'll be tuning the margin by picking a point that has that is classified correctly, but is not classified very correctly, I guess. Yeah. Sure. So okay. So in this case, if you have kernels, kind of the key insight here is that the only way we're interacting with this data, the only way we ever measure the data, other than looking at the sign, is with this is with the dot product. I find either one thing that is misclassified by a dot product, or it's the most misclassified. Okay, and I'm just going to replace this with a more complicated function. If I replace it with the lowest function down here, lowest kernel, this is a polynomial kernel. Basically, I'm finding a polynomial separator instead. It turns out this is equivalent to doing some polynomial expansion, and then it's in a linear space again. But with the Gaussian or like Laplace kernel as the other examples here, then this has another nice interpretation I just want to mention. Okay, so if I treat this as the Gaussian kernel, I'm going to again get some nonlinear separator here. And in fact, it has a very nice form from a geometric point of view, based on the kernel density estimate of the data. So what is the kernel density estimate? Well, I've got a bunch of points, and I replace each of them with a Gaussian kernel, and I add up those Gaussian kernels, and then I take the average. Now in Perceptron, we didn't need to normalize, so I can get rid of this this normalizing term out front here. Okay, but it's basically just I'm adding together things, and that's a kernel density estimate. And here's a better picture generated in Python, where you actually draw the kernel density estimate of the positive points, and I'm and those show the values in blue are positive, and I'm subtracting the kernel density estimate of the negative points, And where that function value of the difference between these two kernel density estimates is 0 is exactly the separating function. And so this is where it gets it's nonlinearity. So the separator has to be the ISO level of one of these, you know, kernel density estimate functions. Okay, and that's a nice interpretation. And I'll come back to this a little bit later in the talk.
This is something like a valley in the among the hills kind of thing, like.
Well, it's
Valley
not a
point.
valley. So the red ones are these pools, are like a lake, right?
Okay.
Is the minimums, and the blue ones are the hills. So it's not
Okay.
really a valley. It's
Oh
not,
yeah, it's not actually, yeah.
yeah. So think of it as like the Bonneville Shoreline Trail, right? Where, you know, the Bonneville Shoreline Trail is basically flat. So you're nice biking along there, and you got the mountains going above, and everything below is in the city. Everything above that is national forest. You can't build houses there or something. Everything below, we've built a lot of houses, right? Yeah. So great. So okay, so there's this kind of nice geometric interpretation. There's another interpretation where, and I'm not going to go into the kind of the details of how this works so much, but you can think of this as mapping to this function space, this high dimensional space, and then it's again linear in this space. But the image of that on the original d-dimensional space is going to be nonlinear. And there's an inner product in this lifted space, and if it is if at this r degree polynomial, I think it's actually should be r to the d dimensions, not r times d. But if I have a Gaussian kernel, I can do this, but it's actually requires an infinite dimensional space. But there's these approximate maps that say I can do it with an additive epsilon error with 1/epsilon² dimensions. And this was like the test of time paper from NeurIPS 2007 that kind of showed that you can do this. A way to think about this is it's actually these elements of this high dimensional space are actually kernel density estimates, right? I can evaluate them anywhere. Because I can evaluate them anywhere, each place I evaluate is one of the dimensions effectively of the space, and I can infinite number of places I can evaluate, so I get infinite dimensions. So that's the way I like to think of it. Not going to get into that geometry. I'll mention some of my recent work has been trying to turn this additive error of Rahimian rect into a relative error here, and we've basically succeeded in mostly solving this problem recently. Okay, with basically the same number of dimensions, but it's more costly. So that's one way to do it, and this was kind of up to about 10 years ago. This was kind of the most popular way of approaching these non-separable problems. Well, I don't know if that's necessarily true, but I mean it was one very, very popular way of doing this. Another approach is to penalize it. And to say, I don't just want to count, say, how many things are misclassified, but actually penalize things for being classified. The more misclassified it is, the more the penalty. So I look at the separator, these Q2 and P5 are misclassified, and then I'm going to look at this purple line. The longer that purple line, the more penalty that point is causing. Okay, and this penalty was called a loss function, the L function here, usually some prior also on some separator. I don't want complex functions. Okay, and so there's this cool form where if I, again, take a dot product multiplied by the sign, I get some value. And the way to interpret that is the z value, if it's positive, I get a penalty of 0, it's not misclassified. If it's negative, I get a penalty of 1. Okay, the problem is this function is not convex, and this will be an issue. So instead, you replace it with one of these loss functions, which are convex. There's like the hinge loss function, the smooth hinge, the squared hinge, the logistic, and the ReLU is like a shifted version of the hinge. These are all kind of approximations of this, but now are these convex functions. And what's nice about this is if I use the linear inner product or a kernel, which is positive definite, like a Gaussian kernel, then this f of x function, remember this original function here is a function in the parameters, the d-dimensional parameters of the half space. That's a convex function. Okay, so the fact that the loss function is convex ends up meaning that this entire function is convex. And there's this other old line of research in optimization. And if we know if we have a function we're trying to optimize, a function of the penalties of all the data points, and it's convex, or especially if it's what's called strongly convex, then you can use gradient descent to converge very rapidly towards the optimal point. Okay, and this is the case for all of these formulations, and that means that we can take the derivative of this and then basically walk in the direction of the negative derivative, and we walk towards the optimal parameters of this cost function, and this is how law of machine learning works. Okay, so to a hopefully, if you've seen machine learning, this should not be so new. To kind of a from a geometry perspective, there's kind of some twists and turns along the way here. So I'll mention just briefly their connections to things saying geometry. Subgradient descent is akin to this Frank-Wolf algorithm, also from machine learning, but this goes to these, similar to this idea of coresets, which are popular in computational geometry for other problems. And stochastic gradient descent is where you move in the gradient of just one of the data points at a time. Both of these have in common that they reach an approximate minimum with a small number of steps, but each step only involves one point. So again, it means I only need to look at a small number of points in order to solve the problem. Okay, so I don't need to look at all the data if I use either Frank-Wolf needs to scan all the data. It's like the Gilbert's or Perceptron algorithm. It always takes the most extreme point, but the stochastic gradient descent takes a random point. So I end up only need to look at a small number of random points in order to solve this problem, which is an interesting perspective as well. Okay, so this brings me to the next kind of thing I want to take a little bit of
I have a question.
Yeah.
In the previous slide, so we have this very different kind of loss functions, and there is only one. If there's a convex function, we know that there is only one global minima. So why do we have so many functions? Like, is it because like the optimization may be working better with like the algorithm which we have, maybe tuning better with one of the loss functions, or why do we have to have a different kind of loss function? Ideally, we can take any one of these and use it to get to the right answer.
Sure, yeah. So you're talking about hinge versus smooth hinge versus square hinge. Yeah.
Yes.
So the hinge function is the convex function closest to this delta function that we want. Okay. Yes. However, it has this point of discontinuity, which makes it a little bit annoying, and it breaks certain properties that you might want about convergence of gradient descent sometimes. Usually in practice it doesn't, but in principle it could. So a smooth hinge basically squares this, but it's not quite as good of approximation. The squared hinge is 3 components where it's squared here, but then it's straight again. Oh no, this one's just squared. This one is squared only here, but then it's straight again here. So this one has 3 case points of it, but it's smooth everywhere. It's differentiable everywhere, but you have case statements. And then the logistic is the best smooth approximation of the ReLU, and the ReLU is just a shifted version of the hinge. So they kind of, there's this trade-off of, do I want to deal with case statements? If I don't want to deal with case statements at all, then I want to go with like the logistic. If I'm okay to do that, then the best approximation is the hinge, but maybe I want it to be smooth everywhere, and then there are these other options. So I think that's how they evolved, and empirically sometimes one works a little better than the other. I don't totally understand the nuances of that.
Okay, thanks.
Yeah. So I want to talk about this problem of how many data points do we need to solve a machine learning problem. And this is another story that has a very old and deep connection between geometry and machine learning, where a lot of the machine learning was basically, it started off kind of, I think machine learning, and then went to both communities and found lots of uses in both before coming back together again, as it turns out. And so this is often done through what's called VC dimension. And again, and this is all predicated on whenever we prove something about machine learning, or almost always, we assume that the data is drawn IID from some unknown distribution mu. This is the basis of cross-validation. You have to assume this, and this is the basis of any sort of learning theory. Okay, and we want to predict the expected. So if we have some function, a classifier function g, that the expected value of the sign is the same on a new point drawn from the same distribution. So this is the model that almost all of learning theory is analyzed under. Okay, so how much? So one thing is think, well, then if X is a random sample from you, how big of a random sample should we have, right? So that we can think about means if we have a fixed random sample, how much should we trust it? And if we can keep drawing, we have a really big one, we don't want to look at all of it, when can we stop looking at it? Or if we have to actually pull probes individually, say using you know, mechanical Turk or something, how many do we need to pull, right? Okay, so, and this is defined, I'll define this geometrically now. You may have seen this defined from function classes or something else, but we'll find geometrically with what's called a range space, which is the data set X, could be points in RD, could be something else, but let's say points in RD, and then a family of subsets. And typically often these family of subsets can be defined geometrically, right? All the points defined by a half space, or all the points defined by a rectangle, right? If this is the rectangle, then this is a valid subset, the points inside. But adding these points and this point over here would not be a valid subset if it's, because I can't define those exactly with one rectangle or a disk or something else like that. Okay, so then there's this notion called VC dimension after, so Vapnik and Cherveninkas from '71. Vapnik, one of the fathers of machine learning, so this new parameter looks like a squiggly V. New is the largest subset of points, so I can shatter every coloring. So for every possible coloring of positive or negative or red or blue in this picture, I can find a half space that separates them. So for any 3 points, any coloring, I can find a half space that separates them, but I can't with 4 points. So if I look at these 4-point configurations, I cannot separate the red points from the blue points with a single half space. Okay, so the VC dimension is 3. Okay, so this is a combinatorial, very combinatorial geometric definition. And so it's played a huge role in computational geometry as well. In the early 90s, there was all this work on sublinear range searching, which is I want to ask a query. Let's say in this picture here, I want to return all the count, how many points are in the disk without looking at every single point to check if it's in the disk. Okay, I want to build a data structure that does this. In 1D, a binary tree basically does this with intervals, right? But in 2 dimensions with other shapes, how do I do this efficiently? And it turns out that you can do this as long as the queries you're willing to make have that range class has finite VC dimension. I can make it sublinear as long as that's the case. And this was kind of very surprising result from the early 90s in geometry. Other things with approximate hitting sets and a variety of other things, this has played a very deep role there. Okay, so one of the concepts that ties them together is what's called an epsilon sample, or sometimes called an epsilon approximation of a range space. But this is where it's a subset of the full data set. So now look at the red points in the figure there. So that for any range I choose from some bounded family of ranges, I approximate the fraction of points in there up to some epsilon error, okay? For any query I make. Now, if I make weird gerrymandering queries, I can't guarantee this, but if the class is controlled somehow, then I should be able to do this, right? And so if the ball contains 20 out of 80 points there, that's about a quarter, and I have 4 out of the 16 red points, then I have the right answer. Maybe I have 4 out of 20 red points. I didn't count them ahead of time, then it's approximately the right answer. And if that error for any range is bounded by epsilon, which is say 10%, then it's an epsilon sample. Okay, so what's known in machine learning, we think of these ranges as classifiers, like linear separators are just half spaces, right? But it could be a polynomial or something else. And the ground set is either points or is samples from this. What's known as an epsilon sample, and this is what Vapnik and Chervenikis proved, they originally had a log factor, which was removed later. But basically, an epsilon sample says if I have the VC dimension over epsilon squared samples, I have this guarantee if I choose them at random. Turns out you can do slightly better using geometric techniques, but they're not random samples. We'll talk about this. And this is what has properties in what's called agnostic learning, which means that if you have a classifier and figure out what is the optimal classifier from that class in terms of the number of misclassified points. If I have a sample of this size, then I can find a classifier that has at most epsilon more error than that one by just looking at the sample. Okay, so I can be within additive epsilon, say within, if it's epsilon's 5%, within 5% error of the optimal one in that class by only a sample of this size. And this is entirely controlled by the VC dimension and the amount of error I'm willing to determine. There's also another concept that I think is less known in machine learning, but came from a concept called an epsilon net. This was defined by collaboration between David Hausler, who went on to do a lot of great stuff in learning theory and then in machine learning on genomics, and also Emil Welzel, who's a kind of a father of computational geometry. And this idea is it's a weaker property. If I say that for every range now that contains at least an epsilon fraction of points, I want my sample to contain at least to be in that range. So any large enough range query has to have at least 1 point. I don't need to approximate the ratios, but I just need to hit every large enough range. So this is a strictly weaker property. But it turns out for perfect classifiers, if I assume there's a perfect classifier, then to find a classifier which is only epsilon more error, effectively the same property as before, now I only need V over epsilon log V over epsilon samples. Okay, I don't need V over epsilon squared anymore. And then this is a pretty big difference. If it's 1% error, that goes from a factor of 100 to a factor of 10,000, right? So, or ignoring the log factor, but it's a pretty big difference. And so I have this kind of stronger property if I can assume a linear separator, which might be true for quite high dimensional data. So this is another deep tie between geometry and machine learning. So in the context of this, let me mention a couple of my results, just recent results briefly. So there's this old problem, the maximum disagreement problem, and this is typically not how these problems are solved. But let's say I want to find the half space that, and there's no perfect classifier, and I want to find the half space that minimizes the, it should be the half space that minimizes the number, this maximizes the number of points that are classified correctly. So minimizes the amount of error. Now this is a combinatorial problem. This is not convex anymore. This is that blue delta function, not convex. I can't run gradient descent. Okay, so this is, I can check all combinations of d+1 points again, effectively for half spaces, but that's a big polynomial. What if I want to do this approximately? So I'm only up to epsilon error, the same guarantee you get with these epsilon sample sort of stuff. How fast can we solve this problem? Okay, so we had a paper a couple of years ago that said you can do it in 1 over epsilon to the d plus 1/3. So 1/3 in the exponent with some polylog, some log to the 1 or 2 or something like that. And then we have a paper under review right now where we get rid of this 1/3 and we show in 2D this is probably optimal. Okay, so if you do want to solve this combinatorial problem, we have finally, after many years, I think we finally have what's probably the up to log factor is the optimal algorithm. But this is again why people don't do it this way, because it's a very hard combinatorial problem. So, okay, so let's mention another thing. You could think of another range space where you have some function. Think of now like a kernel function and take a super level set. Anything above a certain level is inside of a range. Okay, and right, so and then for so we want to understand things about and for a kernel, the super level set is going to be always a disk. Okay, but you can imagine other functions as well. And so we have a result from about 10 years ago that if the super level set functions, if like disk, if those have VC dimensions that are bounded, then a sample on that data set will also approximate, an epsilon sample on that data set will also approximate the kernel density estimate. Okay, the kernel density estimate is not just one super level set, but all of them, but we can guarantee epsilon error on this also. And so something I realized more recently is that this means this is a guarantee of plus or minus 1 on the margin of a kernel SVM, right? This kernel kernel version of this classifier. So if and this will be true for any radial basis function that has the super level set as a disk. Sure. So okay, so I won't dwell on these. Let me just conclude with a potpourri of things, and I'll mention little things in natural language processing. So there are many other types of classifiers for people in geometry that may not know, but for one is a KNN, you look at the K closest neighbors of the query point and vote on those. And nearest neighbor searching is a very kind of deep topic in computational geometry. There have been hundreds and hundreds of papers looking at this problem. So decision trees is another thing where you're basically decomposing the space one coordinate at a time to try and get almost kind of uniform within each of the cells, and it looks the same structure as a KD tree, which is a kind of a range searching structure in computational geometry studied very heavily. Random forests, which are one of the kind of best performing ones now, are just mixtures of these kind of sorts of decision trees in some clever ways. With how they do the mixtures has connections to approximate hitting sets, another topic. Okay, so deep neural networks are much more complicated. But one way to think about them is that they're layers of these perceptron algorithms over and over again, these linear classifiers, and they're just joined together. And so at 2 layers, this gives you this piecewise linear classifier in the original space. If you go to more and more layers, it becomes more complicated. One thing that's different, and with random forests and deep neural networks, is that kind of about 10 years ago, we gave up on trying to ensure that all functions had to be convex. We said, okay, let's run on some non-convex formulations. And turns out we have a lot of data now, we have lots of computers, and it turns out it works. So that's kind of a way to explain to geometers what's changed in the last 10 years. Why that's the case, I think, is pretty interesting, right? So how can geometry help? It can help in understanding these non-convex optimizations, the properties of these function classes that might be useful. Are there generalizations of VC dimension that explain why these work, or other reasons? Kind of, is there implicit regularization in some of these things? The idea of the geometry of the data, I think, plays a role. One of the reasons it seems to actually work much better than what VC dimension would tell us is that the data seems to be nicely shaped, and we basically have enough data to have, maybe not all the data, but enough of a picture of data to know really good sense what is in there and what's not in there. And there might be some dimensional reduction effectively going on in these classifiers. And understanding that how this works with adversarial data, I believe, is again a very geometric problem again. And there's been some work at the intersection of this. Okay, and then let me just wrap up by mentioning a little bit of recent work and directions we're working on. I've done in understanding bias in data and algorithms, and this has come in these word vector embeddings. And so I know a lot of you work in NLP here, but if you haven't seen these these are ways of taking this huge corpus of text, say all of the internet, and they've done this for all the text they've scraped on the entire internet, and they've used it to get a picture of what every word is based on its context of every time it appears. And they embed every word into a 300 dimensional or so space. It has a property that car and truck, which are used very similar in similar contexts, end up being very close to each other. So this is the original goal. Things that appear in similar contexts should be close to each other in this embedding. Things that are not similar contexts are far, effectively. That was the goal, but there was other structure that was observed, which is pretty cool. One of them was these analogies that if you take a vector from woman to man, and then you add that onto queen, this is called a parallel transport in kind of differential geometry, then you get close to the vector for king, right? This blue vector translated goes from queen to something close to king. You kind of get like this structural analogy. And this implies some sort of linearity property going in the space here, which is it's pretty cool. And so one of the strongest, and we've been looking at these linear and other structures in here, and clearly one of the strongest properties in the space tends to be gender, right? So woman to man, queen to king, it's kind of, there's a gender direction that if you go in one direction, it becomes more male, and go the other direction, it becomes more female in the space. And this is a pretty easy to identify this, whereas like his and hers, boy and girl, man and woman are kind of man and wife. They also appear on the same axis pretty clearly. But one of the possible downsides of this is that occupations tend to appear this way as well, because historically there's often male are associated with doctors and female associated with nurses, but these are used in almost every NLP application now. And so now if you want to apply, someone's applying for a job as a doctor and they're female, and an automated machine learning thing might not classify them that way because because of this built-in structure. Okay, so one thing has been how can we remove the structure? And we're not the first to look at this, but we came up with a very simple geometric operation, which is just project down to 299 dimensions away from this gender direction. So doctor and nurse are now similar to each other. Men and women are similar. King and queen. I've removed the gender connotation, but because I still have almost all the dimensions, I've kept almost all the rest of the structure. Okay, right. So this is now a component of this, and we've been looking at extensions of this, including ways that we can remove this connotation, say, between occupations and genders, but not destroy the gender structure. So we still know that a queen is typically female and a king is typically male, which isn't necessarily a bad thing. Those are just different names for things. So how can we retain that while also kind of removing this from, say, occupation predictions? So great. So I'll stop here. So hopefully this was a fun tour of a geometric view of machine learning and kind of its past and its future. And if you want to learn more, there's a lot more in this book, or take any class from me and you'll see more of this, although mostly not on the machine learning stuff.
Thanks, Jeff. If anybody has any question.
So I have a question. Yeah, great talk, by the way. I really enjoyed it. You were talking about the Perceptron, and usually I think in practice the Perceptron that is used is the average Perceptron, and also in practice we can see that like independent whether it is like SVN or Perceptron or logistic regression, the systems tend to work to give you like every time when they were well tuned, the accuracies are most of the time are the same. I was trying to understand if there is a geometric intuition and why that happens, or maybe the fact that Perceptron is average gives a different interpretation, a geometric interpretation that is closer to to this SVM or something like that.
Oh, hey, can you say again what the difference is with this other more common version is?
So what? Sorry, what part of?
So I guess I'm not. I've heard of some variants of Perceptron, but I don't actually know them.
Yeah, the average perceptron. Essentially you keep like an average average weight vector, the final separator, which is like the average of everything that you have seen so far.
Right.
And yeah.
So this algorithm, I didn't spend a lot of time on the fine details of this, but I'm effectively keeping an average. I'm just not doing the step where I divide, so I normalize it.
Oh, okay, I see.
So
I see.
So basically, what you want to do here is you're adding all these vectors together, and if I divide by the number of vectors, I'm going to get an average one.
I see. Yeah.
Right. So there are varieties. So the Gilbert's algorithm I'm doing is not an average. That one is finding it's basically doing a line search every step. There are versions of that, and I've looked at that more closely in thinking about a one-sided version of Gilbert's algorithm, which is kind of like a one-class SVM problem. But there are versions of that show that sometimes by doing the average step, or there's a slightly different version where the denominator is like n/2 instead of n, and that tends to weight things slightly differently. But these sometimes can have slightly better theoretical performance than in some cases than the ones that are doing that are just doing the averaging.
Okay, I see.
Yeah, so there's some nuances in there. So Martin Yagi, who kind of wrote this paper in 2009, this was his first paper, and then he went on and he's been writing kind of a whole bunch of papers really analyzing these different nuances in these algorithms and when these have different effects. But if you look up some of his work, it'll kind of go into these. There are things where you can take an away step, which is subtracting a point instead of adding it to the average, irrespective of the sign, and this can sometimes make a big difference in what it can be doing. And there's a variety of these nuances that in some cases can have big performance differences. In the cases I described here, I don't think it's a big difference.
I see. Thank you for that pointer. I will check it out. Thank you.
So is Martin Yagi from EPFL, if I'm right?
Yeah, that's where he is now. Yeah.
Yeah. Okay, sure.
Right. Yeah.
Anyway, anybody else has any questions? Yeah. So I have a question regarding, like, I work in NLP, so I think it's good I ask a question in NLP. So this word embedding directions kind of thing. So it has been shown like just removing this gender direction. First of all, like there are directions which are unknown. So maybe if you're removing the gender direction, you may be bringing some new bias in some other demographic factor or another sensitive thing. And also how does it guarantee that the cluster of things doesn't remain, like the bias is still not gone and there is not a new direction which pop up from removing this new like the gender direction. So yeah. Any thought on that? I think I heard a little bit about this from earlier talk, but still, will you?
So there are two things going on. So one, you're referring to this lipstick on the pig paper.
Yeah.
Which looked at this. There's an earlier version by Kai-Wei Chen and a bunch of his collaborators, how to debias, which is not quite doing this. They're doing a projection of a subset of the words, and then they're doing some renormalization of them afterwards. And this is often confused in the literature. Sometimes they say that they're doing this operation, but initially I thought that's what the original paper was doing. And then I discovered it was something different. So we ended up writing this paper. And so the lipstick on the pig paper is a little bit ambiguous in describing which operation it's doing. And I believe they're doing the hard debiasing, this other approach, which is more complicated. And those extra steps are most of what is retaining this bias information when it's doing this step. Whereas when you do this operation, if I were to recompute this gender direction from using the same training, effectively the training set to train it, it's going to be a 0 vector. Or maybe there's some numerical error. It's going to be effectively a random direction, right? So if you do this step, you should not have that problem. There might be some other subtle things because I haven't trained on the right data, and there's other data that's left over that is causing this, and those issues may still be there. But this is more of an issue of how do I do the training and the test data, and which data do I, and some of those other issues. There's been there's starting to be a number of techniques like this, alternatives to debiasing, and I think, I'm not sure we've finally settled what the right way of doing this is, but we're making progress towards that.
Okay, if anybody has another question, or otherwise we can. Okay, so I would like to again thanks Jeff for the time and the useful talk. And we cannot do a physical clap, but we can always do a virtual clap. So everybody, if there's a button of reaction, you can do a virtual clap. And thanks everybody for attending the talk. It was a great talk. Thanks Jeff for the time. And you can also have a feedback if you want to give, or anything else you can email me. Thanks a lot for your time, and thanks everybody for joining.
Yeah.
Thanks.
Great.